Good morning, guys. Let's get started. So today is my great pleasure to host Dr. Feng Qian. He is an associate professor from the ECE department at the University of Southern California, USC. So Dr. Feng Qian has done phenomenal research on mobile systems, AR, VR, mixed reality systems, and real-world system management. Basically, every year he has published tons of research papers on top-tier system networking management conference. And of course, he has won a lot of awards. For example, Connect's Best Paper Award, CCON Best Students Paper Award, and multiple other best paper, the Google Research Scholar Award, NSF careers. Basically, he has won a lot of awards and has done so many impactful research. So let me stop it, and I'll ask Dr. Feng Qian to start his talk.
Professor Gao for the introduction. It's my great pleasure to visit Delaware. So I'm an associate professor at ECE of USC. So I'm mostly a system person. Let me move to the bar of the Zoom. Okay. Yeah, so you can see that my research topics are a little bit diverse, but they mostly focus on mobile systems, networking, 5G, 6G, connected vehicles, some large-scale network systems, mostly collaborating with the industry. Recently, I started doing some practical machine learning systems. But in today's talk, I'm talking about multimedia systems and virtual reality. Yeah, so our story will begin from the virtual reality, which has numerous applications in multiple domains. So a quick background on how VR works. So basically, it's pretty straightforward, right? So a user wears a headset. So the headset will send its real-time pulse to a renderer. Typically, it's a GPU. So the renderer will, based on the viewer's viewing direction, to render frames and send the frames to the headset for display. So some VR headsets also have these controllers, right? So the user can use the controllers to interact with the VR system. So there are some quality of experience, QE requirements for VR, including very low latency, high frame rate, and high quality of the images. So most of the VR systems are tethered, right? Which means that for the headsets, you need to use cables, like HDMI cables, to connect to the PC with a high-end GPU. But we are mostly interested in those untethered mobile VR systems. So for mobile VR, it's the good thing is that there's no cable, and also it's very cheap. So the headset is basically a dumb device, right? So there's no computation power for the headset. You just insert a smartphone. All the computation and rendering capabilities are on the smartphone. So another taxonomy of the VR is a local versus network VR, right? So for local VR, so the content is just hosted, stored locally, like on your PC or on your smartphone. And for network VR, which is obviously more flexible, is that the content is stored remotely on the cloud, right? And you need to stream the content in real time during a VR session. So if you apply these two taxonomy, right, so we can draw a 2x2 like a Rubik, right? So there are different types of systems. So local tethered VR, local mobile VR, network tethered VR, and network mobile VR. So the state of art is the local tethered VR, right? So for example, if you buy those VR games from Steam, so you have to download everything, and you need to have a high-end PC to run these VR games. But my recent research focus is the networked mobile VR, which is probably the most challenging scheme for among these four schemes. Right? So there are a couple of challenges. For example, those mobile devices, they have limited rendering power. And also because you're doing streamed content wirelessly, so the wireless bandwidth is often fluctuating. And also there are heat and energy issues. So now let's talk about the immersive content streaming, right? Which is a very important application of VR. So it's a key building block of telepresence and holographic communication. So let's begin with the regular 2D video, right? So this is something that we watch every day on YouTube, right? So this regular 2D video has so-called a 0 degree of freedom. So which means that the viewer has no control on the spatial dimension. right? So then we have a different type of immersive content, right? So one of these is this 360-degree panoramic video. So the user has 3 DOF, so the user can rotate her head in 3 dimensions, yaw, pitch, and roll. And also we have this light field video, which is kind of similar to 360 video, but the freedom of movement is somewhat limited, right? So we can call it 2.5 UF. And the most exciting thing probably is this volumetric video, right? So you can see that the user has 6 degrees of freedom. So the user can not only rotate his or her head, but also freely move, like making these translational movement in the space. However, to stream these content, immersive content over the wireless network is very challenging because these content are very hungry for network resources, right? Take the volumetric video in the previous slide as an example. So every frame of the volumetric video is a full 3D model, right? So the 3D model is represented using 3D point cloud or 3D polygon meshes. So depending on, for example, the density of the point, so you can see that if not compressed, so the bandwidth requirement is from about 400 Mbps to up to 8 Gbps. Even after compression, you can see the bandwidth requirement is still pretty high, right? So much higher than today's like YouTube video stream. So another challenge is the computation resources, right? So we know that for regular 2D videos, so there are dedicated hardware that can encode and decode 2D videos like H.264, H.265 encoder decoders, right? So they are embedded in hardware. But for these volumetric content, so at this moment, there's no hardware encoder decoder. So you have to do everything using CPU, which is of course very expensive. So the research question I'm trying to address is how to make immersive content streaming resource efficient while maintaining good quality of experience. So in this talk, I'm going to talk about my research over the past 5 or 6 years, on improving the resource efficiency, improving the robustness, and improving the image quality for delivering these immersive content. So the first project I'm going to talk about is called Flare, right? So this is a very old work, almost 5 years ago. So it's a viewport adaptive mobile 360-degree video streaming system. So let me just give you additional background on this 360-degree panoramic videos. So as I said before, so it can provide users with this panoramic 3 DOF views, right? So you can imagine that the user is sitting in the center of a virtual sphere, and the content is displayed in a viewport that is projected on this sphere, right? So as the user changes the yaw, pitch, and roll, so the viewport on the virtual sphere will move correspondingly. So these 360-degree videos are captured by these omnidirectional cameras, which has multiple lenses that cover the whole panoramic dimension. So this is a frame produced by this omnidirectional camera, right? You can see that it's like a world map. It covers the 360-degree longitude and 180-degree latitude, right? So this is a raw panoramic frame that is encoded and delivered to the player. And also at the runtime, so the headset has sensors, right? So which can measure the viewing direction in terms of latitude or longitude. And also we know the field of view size, right? And based on that information, so the player will run some projection algorithm that project a portion of this large panoramic frame to the display. So in terms of this projection algorithm, right? So the mostly widely used projection algorithm is called this equirectangular, which actually has a very long history, more than like 200 years. So basically, it's the same technique for producing a world map, right? Basically, you have a sphere. You put the sphere into a cylinder and do the projection. So then you expand the cylinder, then you get the world map, right? This world map is basically something that is encoded and transmitted to the player. But another algorithm is called the cube map, right? So instead of putting the sphere into a cylinder, we put the sphere into a cube. So a cube has 6 faces. If we expand the 6 faces, we can get a sort of like different world map, right? But the high level concept is kind of similar. So now let's talk about this traditional 360-degree video streaming. So traditionally, so it inherits almost everything from regular videos. So 360 video streaming has the same encoding scheme. have the same bitrate adaptation algorithm, basically depending on the bandwidth. So you can adapt the quality, right? Like you see same thing on YouTube. So when the quality, when the network is bad, so it will reduce the resolution like from 1080p to 540p, for example, right? So this bitrate adaptation algorithm is also similar. So it has the same client and server infrastructure. And most importantly, so it takes a viewport agnostic approach, which means that the client simply downloads the entire raw panoramic frame, regardless of the user's viewport. So in other words, the only difference between 360 video streaming and the regular video streaming is the projection algorithm, if you consider like YouTube panoramic video streaming systems. So now let's talk about our research, right? So we propose something called the viewport adaptive streaming. So the key observation is that we find the human head motion is to some extent predictable, right? So we have validated this by doing some measurements. We collect a lot of the users' real motion data. So we'll talk about this measurement soon. But if you just take a quick glance, right, we just use very simple prediction algorithm, like a linear regression, we can find that if I want to know in the near future, like next 0.1 second, so it's can be accurately predicted for the viewer's motion, right? But if you want to predict in the long term, I mean, the error will of course increase significantly. So then the resulting idea is so-called viewport adaptive streaming, right? So remember that for traditional streaming, so the content, the client just downloads everything, right? So it downloads, prefetches the whole panoramic content, but it only renders the viewport, right? So in other words, most of the downloaded content is wasted because they are not consumed by the viewer. So in our scheme, so the system will do some prediction, right? So it will predict the future viewport. And based on the prediction, it only prefetches partial content that is predicted to be falling into the viewport, the future viewport, right? So then, because we only download part of the content, so the network bandwidth usage is drastically reduced. And then the client will just only render the viewport, right? So this idea has been adopted by many network VR papers as the basic idea. So now, given this idea, because I'm a system person, right? So I'm thinking about how to build a real system that instantiate this idea. So we then have this flare system. So it's a full-fledged viewport adaptive panoramic video streaming system. So this diagram shows a video chunk, right? So basically for example, if you stream videos, right? Usually the video is chopped into multiple chunks. So a chunk has a fixed duration, for example, 1 second or 2 seconds. And let's say we want to stream this video in 60 FPS, 60 frames per second. So each chunk will have like 60 frames. So then what we do as a pre-processing is we're gonna segment this panoramic video chunks into tiles spatially, right? So a tile just occupy a small portion in the whole panoramic frame chunk spatially. And each tile can be independently decodable and downloadable. So then we have this very nice formulation of an online scheduling problem. So the input of the problem is the predicted motion. Remember, I talked about the predictability of the motion, right? So we have the predicted motion and also the predicted network throughput. So the output we want to schedule is which tile to fetch at which quality levels, right? So there are two dimensions, the quality dimension and the spatial dimension that we want to optimize. So the objective, we want to maximize the viewer's overall quality of experience. So the challenges include, for example, we have a very large solution space, and also we want to achieve real-time scheduling. So now let me just quickly talk about how we do the scheduling in the spatial dimension. So this is a timeline, and the current time is T0. And we do scheduling at a very fine-grained, very fine granularity. For every frame, we want to do the scheduling. So then we continuously predict the motion in terms of both latitude and longitude, right? So this is a predicted trajectory in the next, for example, 1 or 2 seconds. So then, because we know the projection algorithm, we can map from these predicted latitude and longitude to the corresponding tile in the panoramic chunk, right? And we can compute these mappings from the latitude or longitude to the tile position offline, because we already know these prediction algorithms such as equirectangular beforehand, right? So then we know that for each chunk duration, what are the corresponding tiles that we want to fetch? But we do have a problem because the prediction is not perfect, right? So the prediction can make errors. So to tolerate these prediction errors, so what we did was we fetched additional tiles. We call them out-of-sight tiles, right? So this yellow region is the predicted viewport, right? You can see that it occupies 6 tiles, but we fetch additional tiles surrounding this predicted viewport to compensate the potential errors of the viewport prediction, right? So we call them out-of-sight tiles because if the prediction is perfect, then these blue tiles will not be consumed. But if the prediction is not perfect, then we may want to consume such blue tiles. And we dynamically adjust the out-of-sight tiles based on, for example, historical prediction accuracy. Okay, so now let's go through the whole system of FLAIR, which is quite complicated. Because of the limited time, I only briefly talk about the system, right? You can see that most of the logic is implemented on the device, mobile device. So the headset has sensors, so it captures the real-time head movement reading. And we have a viewport prediction module. It uses very lightweight machine learning for high frequency prediction. We basically just use linear regression, which is pretty much the easiest machine learning algorithm. So then we separate the optimization into 2 dimensions, right? So the spatial dimension, which determines which tiles to fetch, and the quality dimension for each tile, which quality to fetch, whether it's 540p, 720p, or 1080p, right? We separate these 2 dimensions. So then we have this algorithm in the previous slide for tile selection. And for the quality dimension, we also come up with quality of experience metrics for 360-degree videos, and we come up with a rate adaptation algorithm. So then the requests are sent to the server. So the server will just return to the client these encoded tiles. So we also did some system level optimization. For example, we find that on mobile devices, they have these multiple decoders, right? Because we want to decode multiple tiles concurrently. So we use multiple asynchronous decoders for high performance decoding. And also we cache the decoded frames for smooth transition between tiles. And we also introduce some networking optimization. We optimize the TCP/IP stack in the operating system for quickly adapting to the network, to the head movement. And we managed to integrate everything together into a holistic system on smartphones. So next, I'm going to show a video. Unfortunately, I'm not able to play the sound, but I just explained this 1-minute video, right? So it's the demo video we presented at the conference. Yeah, so the basic idea again, so first 360-degree panoramic video streaming is very important. So it provides users with panoramic views with 3DOF, but fetching everything is very expensive. So the high-level idea is viewport guided streaming. So, so we do the prediction, and we can prefetch portions that the user is about to see, and run the projection algorithm to get the view. So we target commodity mobile devices. It reduces the bandwidth, improves the video quality, and we innovate the end-to-end streaming pipeline and integrate everything into a holistic system. And we do a lot of extensive experiments on real devices and real networks. Right? And here, so the bottom one is our streaming effect, and the top video is the state of art. You can see that the state of art was pretty choppy at the time. And our system can smoothly stream 360 videos with much lower bandwidth usage. Okay, so this is the first piece. So the second piece, so we did this work in 2019. So we're gonna try to further improve the viewport prediction. So remember that FLAIR takes a very simple approach. It's just for individual users. It just performs short-term prediction, right? It just uses a historical window of the previous motion trajectory using very simple machine learning like linear regression to predict the future window. So another opportunity for prediction is that we can do crowdsourcing, right? So here, for example, here we show a panoramic frame, and we overlap some heat map, right? So the heat map is we get it from 30 viewers' viewport position, right? You can see that in this safari zoo, right? Most of the viewers just look at these elephants, which is obviously expected, right? So if we have this crowdsourced data of the user's viewport, right, we can potentially leverage such crowdsourcing for long-term prediction. For example, in the next 1 minute or 2 minutes, right? So if we have this long-term prediction, we can leverage them to further enhance the viewport adaptive panoramic video streaming. So then to validate this hypothesis, so we conducted some large-scale data collection. So we picked 10 popular YouTube 360 videos, and we collect a lot of data from more than 200 people, right? You can see from this breakdown, so these people are pretty diverse in terms of the gender, experience, and age. And also we collect data from people using with different interaction methods, right? So most of the users, more than 130 users are using headset. And some users use phone, right? Because phone also have sensors by like just moving the phone. So we can also watch panoramic videos. And about 100 users, they just use PC, use mouse and trackpad to navigate the viewport. So we collect a lot of viewing sessions from 275 users with a lot of playback time. So then we begin with, again, single user regression for viewport prediction. So the idea, again, so given the trajectory in HW, historical window, so we predict the trajectory in the prediction window, right? So in this diagram, so the historical window is 1 second. We want to predict the next 4 seconds. So the training and prediction are both done online at runtime. So we use, again, simple machine learning, including linear regression, multi-layer perception, and also we have a static baseline, right? So the static baseline, we just assume that the user doesn't move. In other words, the last viewport in the historical window doesn't change. And we separately predict the latitude and longitude. So then for the crowdsourced learning, so we just build a simple deep learning framework using LSTM. So it has one subtraction layer for first point normalization, one LSTM layer with 64 neurons, and one add layer that restores the predicted values. And the training is done offline using about 30 users trajectory. And we build one model for each video. And the inference is, of course, online. I don't have time to show the figures, right? But here are high-level prediction results, right? In terms of the prediction difficulty, obviously, the longer the prediction window is, the more difficult it is to predict the future viewport. And also, we find that the horizontal movement is more difficult to predict compared to the vertical movement, right? Because most of the users just rotate the head horizontally instead of looking upwards and downwards. And the regression models only work well for the short prediction window. And we find that the static baseline performs surprisingly well for the long window, right? Because if the user doesn't move, then the static baseline will win. We also find that this crowdsourced learning, it consistently outperforms both a regression and the static baseline. And we found that 30 users is pretty much sufficient, right? Adding more users just marginally improves the prediction accuracy. And in this case, we need edge or cloud support, right? Because even for inference, because we're using LSTM inference at 60 frames per second, so that is quite a high frequency. So the device, mobile device, they are just too weak to perform such inferences. So here we see an example of the crowdsourced prediction, right? So here, so the dashed line is the ground truth, is the true movement trajectory. And the blue line is the sequence-to-sequence prediction, where you can see that the blue line largely matches the ground truth. Also, we find that the different interaction methods matter. Right? Remember that in our data set, right, we have different interaction methods using VR headset, using VR smartphone, and also on laptop and PC, right? So we found that the VR headset movement is the easiest for prediction because the movement when your head moves is very smooth, concentrated trajectories. On the other hand, So the laptop or PC movement is the most difficult one, right? Because you can see that the viewports are scattered and discrete, right? So think about how you navigate using your mouse or trackpad, right? You move, then you pause, then you make the next movement, right? So these like sudden stop and move, stop and start and stop makes the prediction quite difficult. Okay, so this is the second piece of work. So we try to use crowdsourcing to further improve the viewport prediction. So the third piece of work, so we further try to apply this viewport adaptive streaming idea to volumetric videos, right? So this work was done in 2020. So just a recap on the volumetric videos, right? So it provides the users with 6 degrees of freedom movement, right? So the user can not only rotate the head, but also freely make translational movement. So every frame of the volumetric video is a 3D point cloud or polygon mesh. So it's fully 3D, and the user has 6 UEF. So these volumetric videos are captured by RGB D for depth cameras. So you need multiple depth cameras to capture the whole panoramic scene, and these cameras need to be synchronized. And it has many applications, like entertainment, medical, education, and so on. So now let's consider apply this viewport adaptation idea for volumetric videos with 6 UF. So because volumetric video is 3D, right? So we need to change some configurations, but the high-level concept remains the same, right? So one thing, so the 2D tiles now become 3D tiles, right? So each tile is like a 3D cube or cell. And also we need to do 6 UF viewport prediction, not only predicts the rotational movement of the head, but also predicts the translational movement of the user. But we can actually do more, right? So there are new optimization opportunities for volumetric video streaming. So we call them 3D occlusion and viewing distance. So for the occlusion, because it's in a 3D environment, right? So some tiles may block other tiles, right? For example, these blue tiles in the front may block the green tiles in the back, right? Because these green tiles in the back are either partially or fully blocked, so we can reduce their point density to reduce the bandwidth consumption, right? For example, if you stream these blue tiles with 100% point density, you can just stream these green tiles with 50% of the density without affecting the quality of experience, right? So we call this optimization dimension occlusion visibility. So another dimension is called this distant visibility. Sorry, it's blocked by this message box, but it's called distant visibility. So the basic idea is also straightforward, right? So if we view this baby from a long distance, like 5 meters, so we can reduce the density of the point cloud to save the bandwidth, right? Because this baby is small in the projected view, right? So we don't need such a high point cloud density. But if the viewer moves closer to the baby, so we'll increase the point cloud density accordingly. So we have some model to determine the density level with respect to the viewing distance. So we show in the paper that by integrating these 3 optimizations, so we integrate these 3 optimizations into a holistic system called a Vivo. And we show that the Vivo with these 3 optimizations jointly applied, so we can achieve up to 80% of the bandwidth reduction with virtually no drop in visual quality. Okay, so this is just a quick introduction for how to apply the viewport adaptation idea to the volumetric content. So the 4th piece of work, we still focus on volumetric streaming, but we are using a different approach called the multi-view transcoding, right? So this is more like a recent work we done last year. So now let's try to revisit different methods for streaming this volumetric content. So the Vivo, the previous work, takes so-called direct streaming approach. So it's straightforward, basically from the video source. So the viewer or the client just downloads the 3D point cloud stream, just download the 3D content to the client, right? So it's called the direct streaming. So another approach, we call it transcoded streaming. So for transcoded streaming, we need an edge or cloud support, right? So the edge because the bandwidth between the edge and the video source is usually abundant. So the edge will download still 3D point cloud. And then what the edge does, it will real-time transcode this 3D point cloud to 2D stream based on the real-time 6UF position, based on what the viewer is looking at. So it will basically render the 3D point cloud or 3D polygon mesh to the 2D view, and then encode and send this 2D stream to the viewer. Right? So there are pros and cons between these two approaches. For direct streaming, so it has high bandwidth usage and high client decoding overhead. Right? Remember, for volumetric content, the client has to decode it using CPU in software, right, which is very expensive. But for transcoded streaming, the bandwidth usage becomes much lower because sending 2D transcoded 2D content incurs a much lower bandwidth compared to sending 3D content. And because it's 2D, right? So the client can just use hardware decoders that is used to decode regular videos to decode this transcoded 2D stream. But the transcoded streaming, it needs the edge or the cloud support, which is fine, right? Because we're using cloud everywhere. But there's one problem. It's called the content fidelity, right? So this transcoded streaming has this viewport inconsistency problem. So which means that the real viewport may oftentimes differ from the viewport of the frames sent by the edge. Right? To see why we have this viewport inconsistency problem, let's look at a simple example, right? So at time t1, so the viewer will send its 6UF position to the edge. So the edge receives the raw 3D data and render the 3D data based on the position A sent by the viewer. And then it sends the rendered 2D image at position A to the viewer at T2, right? Because of sending this data and rendering, they all take time. So at T2, the viewer has already moved to a different position B, right? So then we have this inconsistency between position A, which is reported at T1, and position B, which is the real position at T2. So then the problem is how to overcome this viewport inconsistency problem, right? So our idea is also very straightforward. So we call it multi-view transcoding. Instead of just sending one 2D stream, so the edge will concurrently basically render multiple 2D streams. And then the viewer will just select the best 2D stream to maximize the QE, right? So the analogy is like the ensemble learning, right? Instead of just using one model, we can use multiple models, their synergy to improve the prediction. Okay, so again, so given this idea, we want to build a system to demonstrate that it indeed works. So now let me just give you a little bit more details of how to generate this multi-view, right? So we start with a small number of seed views, and each seed view is predicted by a separate machine learning model. So our prototype just uses 3 seed views predicted by multi-layer perception, linear regression, and also the stationary baseline. So then we construct a convex hull from these 3 seed views, from these 3 seed views, but 3 is still too small, right? So we further expand this constructed convex hull, expand it to construct a 5x5 grid, right? And these parameters that we use to construct a 5x5 grid, we just choose them empirically. So then in this 5x5 grid, we pick 17 candidate viewports. So 17 plus the 3 original seed. So we get 20 candidate views in our prototype. So then we have these 20 candidate views. We try to rank these candidate views using a data-driven model built from a user study. So we asked 30 users to watch more than 100 video clips. So in this user study, right, we basically show 2 transcoded views side by side. So these 2 transcoded views are transcoded using different configurations. And we let user choose which one looks better by how much. And using this data, we basically construct a quality of experience model to give a score to each transcoded frame.
Question.
Yes.
the inconsistency is based on the change of user's position.
Yes.
So that's geographic data.
Yes.
Which part of your optimization or the grid capture that volumetric features?
So here, this grid basically is the geographic.
Is the geographic?
Yes, is a geographic. So they basically visualize the locations. Yeah, so these are the actual physical locations.
This is the map.
Yes, the map. Basically, the viewport. Remember, 6 UF is basically a coordinate, right? So these are just the coordinates. Yeah. Okay. So basically, we use a model to give a score for each candidate view, right? So then the edge just picks the top K views with the highest scores, encodes them, and sends them to the client. So we can dynamically determine this K based on the motion speed, right? Intuitively, if the viewer is moved fast, so then it means there are more randomness. So we use a large K value. So if the user doesn't move or move very slowly, so we can use a small K. So then we have these K views, right? So we just encode them and combine them with so-called the spatial and the temporal arrangement, right? So for spatial arrangement, we just merge these K views into a mega frame and encode this mega frame and send it to the client. For temporal arrangement, we just encode each of these K frames separately and sending them to the client in a stream. So the client-side logic is pretty straightforward, right? So the client just applied the same data-driven model in the previous slide and picked the best view with the highest score. So now let's look at some results, right? So we compare, our system is called the views. So we compare the views performance with Vivo. Vivo is the direct streaming approach I just talked about, right? So here we also did a user study with 32 participants. So on the x-axis, V3, V4, V5, V6 are different volumetric videos. And the y-axis is the bandwidth usage, right? So let me explain each of these bars, right? So the blue bar, single MLP, is the single view transcoded system, right? We just transcode into a single view. So it has this inconsistency problem. And the views S and views T are our system. We basically remember we have different ways of doing the transcoding, encoding, right? Spatial arrangement or temporal arrangement. So corresponding to views S and views T. And the red one is Vivo, right? So we do directly streaming, right? You can see that by sending 3D data, so it consumes almost 1 order of magnitude higher bandwidth compared to our system. So our system can reduce the bandwidth consumption by up to 95% compared to Vivo. And also if you compare these 3 bars, right? So single MLP versus multi-view transcoding, you can see that multi-view transcoding just marginally increased the bandwidth compared to single view, right? So this is because when you are transcoding these multiple frames, so they are very similar, right? So there are a lot of opportunities for compression. So the actual bandwidth usage is not that high. And also we ask the user to subjectively rate their experience, right? So here, so we show the distribution of the MOS difference. So this mean opinion score difference shows the quality of experience between the Vivo and views, right? So if it's negative, like this, it means that Vivo is better than views. So if it's positive, means that views is better, right? You can see that when the bandwidth is sufficient, so people tend to prefer direct streaming because we don't have bandwidth issue here. But if the bandwidth reduces, then the direct streaming will encounter issues because of the limited network resource, then our scheme is much better in terms of the quality of experience. Okay, so this is the 4th piece of work. We further try to come up with some bandwidth efficient approach for volumetric view. So the last piece of work, so we did it this year and it will be published at a conference next year. So it's a system called the habiters, right? So we further try to improve how we can advance the prediction and also make the immersive content streaming even more efficient using this full body pose tracking. So the basic observation we have is there is so-called spatial correlation among body parts during a human motion, right? For example, let's say that you are wearing a headset, right? And you're holding a controller. Before your head movement, oftentimes your hand with the controller moves first, right? Basically, this hand movement will give an early signal of the head movement. So similarly, when you're watching volumetric video, if you step back, your leg moves before your head moves. So then our hypothesis is that tracking this full body pose can hopefully improve the head motion prediction accuracy. Right, so remember, this is our previous machine learning model, right? So we use historical 6D of head motion to predict the future 6D of head motion. So then, inspired by this, we just add a feature of body pose, right? Try to enhance the prediction. So how to get the feature? We use this open pose, which is an open source framework that uses computer vision to extract the body pose of different joints. So let's look at the 25 different joints position. And from these 25 joints position, we select, I think, 10 and use them as the body pose features. And also in this work, we further make some innovations. By augment this model, we use this model not only for motion prediction, but also for network throughput prediction. So we are focusing on this so-called millimeter wave throughput prediction. So we further add features of historical millimeter wave throughput, and we use the same model to predict both the motion and the future millimeter wave throughput. So what is millimeter wave network? Let me just give you some background. So this diagram shows the wireless networking spectrum, right? So you can see that from about 300 megahertz to 6 gigahertz is so-called omnidirectional radio. So our traditional Wi-Fi network, AO2.11, A, B, G, and ACAX, and also 4G network and low band and mid band 5G. So most of the wireless networks you are using fall into this frequency band. So on the high band, from about 15 gigahertz to 100 gigahertz is so-called a millimeter wave band. Right. So we call it a millimeter wave because the wavelength is close to the millimeter wave range. So there are commercial wireless networks that use the millimeter wave network. For example, millimeter wave 5G already deployed by multiple carriers in the US. And also some Wi-Fi standards like AO2.11 ADA-Y, they use millimeter wave. So there are some trade-offs between these two kinds of network, right? So for omnidirectional radio, so the bandwidth is low, but because the wavelength is large, so the signal is robust, right? So it has slow signal attenuation, and the signal is less vulnerable to blockage. So the millimeter wave radio is just opposite, right? Because of the abundant spectrum resources in the millimeter range. So the bandwidth is very high, but the signal is weak in terms of fast signal attenuation, and the signal is very vulnerable to blockages. So what we want to do is to leverage this high bandwidth at the millimeter wave band for streaming this bandwidth-hungry immersive content. So here is some experiments done by T-Mobile. Right? So T-Mobile runs both the millimeter wave cellular network and the traditional omnidirectional cellular network. Right? You can see that this man closed the door. Right? So the glass on the door will become the obstacle. You can see that the millimeter wave signal is basically blocked by the glasses, but the omnidirectional radio is not affected. So we run similar experiments. In a room, we put two wireless access points. So this AO2.11 AC is the omnidirectional radio, and AO2.11 AD is the millimeter wave Wi-Fi, right? And we have a user. The user wears a headset, and we mount a smartphone with dual band, both AC and AD, to the headset. And the user just walk circle in this room, right? So here we can see the throughput at different positions, right? You can see that AC, which is omnidirectional radio, so the throughput is pretty stable, right? For AD, you can see that at certain spots, the throughput is very high, up to 8 Mbps. But at other places, the throughput is low, right? So this is because at these positions with low throughput, so the human body actually blocks the millimeter wave signal. Okay, now let's go back to our prediction problem, right? So remember in the previous slide, so we see that the millimeter wave signal propagation is very sensitive to the motion and to the environment, right? So then it inspires us to basically fuse the throughput, millimeter wave throughput, and the body pose and the 6D of motion, fuse them to also predict the millimeter wave throughput. Okay, so now let's try to build a system to validate our hypothesis. How can we use this motion to help predict the throughput? So we find 4 locations: personal office, living room, university office, and the meeting room, right? So in these 4 rooms, we set up a millimeter wave access point with a stereo camera. So remember, we use the stereo camera to capture the full body poses from this computer vision algorithm to extract the pose of the human body. And we ask 3 viewers with different heights, 1 female, 2 male, and exercise 10 motion patterns listed here. So these are very easy tasks. Just for example, just a walk in a clockwise direction and do some motions to collect some training data for the model. And during the collection, we just collect the 6D wave head motion. We collect full body pose, and we collect a millimeter wave throughput. We use this data to train our model. So here are the experimental results, right? So here you can see that we show different machine learning algorithms using recurrent neural network. So this BP, I believe, is fully connected network. GBDT is a classical machine learning model, and sequence to sequence is a deep learning model using LSTM, right? So we show the prediction errors of the millimeter wave throughput in MBPS. So the prediction target is the millimeter wave throughput in the next 1 second, right? You can see that by using the pose information, so we can reduce the prediction error considerably from 5% to 29% in MAE, being average error, and 5% to 25% in root mean square error. So basically, the conclusion is that using the pose information does help reduce the prediction error. So we have a new problem here because in this experiment, right, we just use a pre-trained model to do the prediction. But in practice, see, using a pre-trained model cannot adapt to the changes deviating from the training data, right? So let's say I have a pre-trained model. So what if I change the location? Using the same pre-trained model may not work. What if the user changes the motion patterns? What if there was some environment change? For example, I just move the furniture in the room, right? So the movement of the furniture will affect the millimeter wave signal propagation. And also there may be some dynamic changes. For example, a person walk by, right? So the person may become an obstacle for a signal reflector. So to deal with these changes deviating from the training data of the model, so our solution is called transfer learning, right? Which is a well-known technique in machine learning community. So basically, after change, we can collect additional training data to update the previous pre-trained model instead of training a new model from scratch. So the key assumption is that there is some environment knowledge before and after change that can be transferred from the previous model to the new model. So such environment knowledge may include, for example, the physical property of millimeter wave or the throughput distribution in certain positions. So through experiments, we found that if we change the location or change the user, so this is considered to be a large change. We need some offline transfer learning. Basically, before the VR session starts, we can ask the user to exercise some additional movement for 1 or 2 minutes and collect some training data, and offline upgrade the model for bootstrapping. So for other changes, like change the movement patterns or some environment changes, so there are small changes, we can just use online transfer learning. Basically, because at the runtime, right, so our system also collects new training data, we can upgrade the model at runtime. So this won't disrupt the user's usage. And finally, so we put everything together into a system. Again, so this system needs edge support, right? So the edge runs the full body pose extraction. It tries to do the model inference to predict the throughput. And also it performs the online transfer learning to upgrade the model. So there's one component I haven't talked about, right? So basically the edge also has this multi-pass scheduler. So it can jointly use millimeter wave and omnidirectional radios at the same time, right? Because the omnidirectional radio is very stable, so it can guarantee the basic performance. And we just leverage the millimeter wave radio opportunistically. And we implement the system using a hybrid of hardware and software. The students did a great job of putting everything together. And also we design application interface, right? Because our system habitus is basically a framework, right? So it can support diverse application runs at upper layers. So the interface is very simple. It just predicts the 6 UF motion and also the millimeter wave throughput. For example, we managed to integrate this habitus with Vivo, our previous volumetric streaming system. We only need to change less than 50 lines of code by incorporating our habitus system. Okay, so this is the last real slide. I still have 7 minutes. So we basically try to evaluate our system. All right, so this slide is a little bit dense, so let me try to walk through it. So basically, we tried different schemes, right? And on the left figure, we compare the stall, basically how frequent the video freezes versus the video quality, right? So AC, this blue one, we only use the omnidirectional radio. You can see that the quality is low because of the low bandwidth of AC. So for AD, we only use millimeter wave radio without any prediction. You can see for this AD, although the quality improves, the stall rate also improves, right? Because using AD, if there's no prediction, then if there's a blockage, then suddenly the throughput will reduce and the system has no time to respond to it. So the simple one, the green one, we use both, combine AC with AD, but still without prediction. In this case, obviously the average quality improves because you have 2 radios, right? But still the stall rate is non-trivial. So Musha VR is kind of want to compare it with some literature, but it has similar performance. So this is a previous paper we compare with. It also doesn't perform any prediction. And the Pro is our scheme, right? So our habitus framework, we use AC and AD with prediction, but for the prediction, we only use 6 UF feature without full body pose. You can see that this Pro already significantly reduces the stall because with prediction, the system has some intelligence, right? It can proactively react to the reduction of the millimeter wave throughput. And the full system, so we have AC plus AD with prediction. And for the prediction, we use all the features, both the 6 UF feature and the full body pose features. So you can see that the full system further reduces the stall and with improved quality. Yeah, and also the right figure, again, so we conduct a user study and ask the users to subjectively rate their experience. We saw a similar trend, right? Basically with full system, so user can actually subjectively feel better quality of experience. Okay, so basically this completes our 5-year journey on trying to improving the resource efficiency, performance, and robustness of streaming immersive content. Right? You can see that for these different pieces, they share something in common. Basically, they all perform motion prediction. But you can see that over 5 years, we managed to improve the motion prediction in multiple dimensions. Right? From a single user to crowdsourced prediction, from the panoramic video, 360 video with only 3 UF to volumetric video with 6 UF. From using a single prediction model to this ensemble prediction, and from just using the head motion to further using full body pose tracking, right? And the joint efforts of these innovation make basically consistently improve the performance, robustness, and resource efficiency for immersive content streaming. Okay, so this is really the last slide, just a quick summary, right? So I feel that engineering this network mobile VR system is really fun. I enjoyed a lot from it. And also, I hope this talk convinced you that this immersive content is the data plane of the metaverse. So it's very bandwidth hungry. So how to reduce the resource usage still remains a very challenging research problem. So through this, these different studies, right? So there are some common design principles that we try to follow. For example, adapt to the network and compute resources, incorporating viewers' motion patterns, and also harness the power of AI through, for example, edge computing. Okay, so I'll stop here. Thank you very much, and feel free to ask questions.
It's very interesting talk. Any questions from our audience?
So, you talk about transfer learning, real time. So, I'm an investor, but how would you ensure that you also have annotation data during that?
Okay, so the question is, so we are doing transfer learning at runtime, right? How to get the labels, right? Yeah, because remember when in a real-time VR session, as you move, you always can get the ground truth, right? You can measure the actual millimeter wave throughput. You can actually measure the actual 6DF motion, right? So you can get the labels in real time. Although there's some time lag, but you can basically get the labels, right? You can use this training data to upgrade the model.
How would you? Because I would say like if you want to adapt in real time, those time lags.
Yeah, but remember the training, right? So we use this label for training. The training can have some time lag. The training doesn't need to be strictly real time. Only the inference will need to be real time.
Yeah. So you probably do the training in the background.
Yeah, the training is on the background at the lower priority thread. So the training can have maybe like 1 or 2 second delay, but the inference needs to be high frequency, really at runtime. The time we allowed for the inference is just a few milliseconds, right? Compared to the training, which we can allow up to several seconds delay.
Is that right? Some related work in a field called test time adaptation. So people trying to do like people trying to adapt to new, distribution shift data in real time using like, and they don't even use like label data. So
Okay.
I don't know if you heard about it.
Yeah, definitely. I think there's some work for we use some like semi-supervised learning to, yeah. I think there's definitely room for improvement. Yeah. Yeah, but good. That's a good point.
Other questions? Let me ask one question.
Yeah, sure.
So I think one of the key ideas for the prediction.
Yes.
And you actually doing very intensive prediction of 60 times per second.
Yes.
Like that. So you need to have an edge server.
Yeah, unless you're using very simple machine learning like linear regression, otherwise you do need an edge support.
So basically, all the content will first download it to the edge server.
Yes.
And then do the prediction and then offload the
Yes.
computing to the smartphone to the edge.
Right.
VR device.
Right.
So I would say it would be very challenging to rapidly deploy everything or implement in the VR system.
Yeah, agree. Yeah. So right now, if you don't use edge, deploy everything on smartphones or like low-end embedded system is very challenging. Yeah. So we do need more research. For example, use very lightweight model, but with good accuracy on these mobile devices.
But you will assume the network connection between the cloud and the edge is actually perfect. Or
yeah, here in this work, we didn't consider, for example, what if there's some disruption between the cloud and edge? I think that's an orthogonal research problem.
So the bottleneck is from the edge server to the.
Yes. Yeah, because it's wireless, right? Wireless, as I shown, like for millimeter wave, I mean, oftentimes you have issues, right? But we assume that between the edge and the cloud, we have wired connectivity over internet. Presumably, it's much more robust, reliable compared to the last one. Yeah, but I agree. So this can be a problem, right? So we also need efficient, for example, compression algorithms. So there's some research on how to efficiently compress using like some advanced data structure or even machine learning, like a super resolution, right, to reduce the direct streaming overhead. I think that's a software work we can apply. Yeah.
Any other question? Okay, no more questions. Thank you again.
Okay, thank you.